Welcome to the course on An Introduction to Information Theory. So today we are going to talk about Gaussian channel. In the last class we talked about entropy for continuous random variable. One of the important channels, continuous values channel, is this Gaussian channel, and today we are going to talk about capacity of a Gaussian channel. We'll first talk about capacity of a Gaussian channel, and we are going to prove the achievability of Gaussian channel capacity. Subsequently, we are going to show the converse to the coding theorem for Gaussian channel, and finally in this lecture we are going to talk about band limited Gaussian channel, and we will compute the capacity of band limited Gaussian channel. So as I mentioned, a Gaussian channel is a very important continuous value channel. If we write its corresponding discrete version, we can write it, let's say if the input is xi and noise is additive, which is Gaussian distributed denoted by zi, what we get as output is yi. This is a discrete version of a continuous valued Gaussian channel. So first result that we are going to show you is the capacity of the Gaussian channel with power constraint P and noise variance N is given by this expression, where the maximum is attained when X is Gaussian distributed with zero mean and variance K. Now let us first look at what is the capacity if we do not have these constraints, power constraints, or if we do not have noise. It's very easy to see if the noise is zero, then whatever we send will be reliably received. So the channel capacity is infinite in that particular case. Similarly, if there is no power constraint, we can make our input arbitrarily large such that it is received correctly at the receiver. So if we do not have this power constraint, then also the capacity of this channel is infinite. Now let us look at the capacity of this Gaussian channel when we do have a power constraint and we do have a noise variance given by N. So from the definition of channel capacity, it's a maximum mutual information between the input X and the output Y, and this maximization is taken over all input distribution P of X. Remember, we have a power constraint here, that's an average power constraint, so expected value basically of X square is less than P. So we need to compute maximum mutual information under all input distribution given this power constraint. So from the definition of mutual information, we can write mutual information between X and Y as differential entropy of Y minus differential entropy of Y given X. Now what, as I said, Y is the output of the channel, which is nothing but input X plus additive noise, additive Gaussian noise, which is Z. So I can write this as differential entropy of Y minus differential entropy of X plus Z given X. Now what's the uncertainty, or what's the entropy of X plus Z given X? That only depends on Z given X. So we can write this expression as differential entropy of Y minus differential entropy of Z given X. Now Z is, which is noise, is independent of the signal X. So the differential entropy of Z given X is equal to differential entropy of Z, because Z, the noise, is independent of the signal X. So we can write this mutual information between X and Y as differential entropy of y minus differential entropy of z. Now we know that z is Gaussian distributed, and if we have a Gaussian distributed random variable, we know what its differential entropy is. So if we assume that z is Gaussian distributed with some mean, let's say 0, and variance n, then the differential entropy of z is given by half log of 2 pi e times n. Now we can compute the expected value of y square. Y is nothing but x plus z, so this can be written as expected value of x plus z square, which is nothing but expected value of x square plus expected value of z square plus 2 times expected value of x and expected value of z. Now since the expected value of z is 0, this term will be 0. So what we would get is expected value of y is nothing but expected value of x square plus expected value of z square. Now expected value of x square is p and expected value of z square is n. So expected value of y square is p plus n. Now we have just shown that the mutual information between x and y can be written as differential entropy of y minus differential entropy of z. Now we know what is the differential entropy of z. That is because z is normal distributed with 0 mean and variance n. So the differential entropy of z is given by this. We also know if y is a random variable which has variance p plus n, then the differential entropy of y is upper bounded by the differential entropy of Gaussian random variable. So we can upper bound the differential entropy of y by the differential entropy of a Gaussian random variable with same variance, and in this case expected value of y square is p plus n. So we can upper bound this differential entropy of y by differential entropy of a Gaussian random variable with variance given by p plus n. Okay, now variance given by p plus 1. So now basically what we have, so this results follows from a theorem that we have proved for differential entropy, that if y is a random variable with variance p plus n, then its differential entropy is upper bounded by differential entropy of a Gaussian random variable with same variance. So clearly this is equal when y is also Gaussian, and y is Gaussian when x is also Gaussian, because y is x plus z. We know z is Gaussian distributed. If x is also Gaussian distributed, then y will be sum of two Gaussian distributed random variable will also be a Gaussian distributed. So in that case y will also be a Gaussian distributed random variable, and in that case this would have been equality. So combining the terms, so this is log a minus log b kind of term which can be combined, so that becomes this. So what we have shown is mutual information is upper bounded by half log of 1 plus p times n. Now remember, the maximum is obtained when x is also Gaussian distributed with mean 0 and variance p. In that case, as I said, y is also going to be Gaussian, and this inequality would be equality. So what we have shown is capacity of a Gaussian channel with power constraint p and noise variance n is given by this expression, where the maximum is attained when The input x is also Gaussian distributed with mean 0 and variance k. Now we are going to show the achievability of this. So all as long as we choose rate less than this capacity, we are going to get reliable communication. So let us prove the achievability part of this capacity theorem. So we are going to use the same ideas that we have used earlier to prove Shannon's noisy channel coding theorem. The difference here is now, in that case we had discrete random variables, here we have continuous random variables. This is another difference. Here we also have this average power constraint, which we did not have when we prove Shannon's noisy channel coding theorem. So we are going to use the same ideas as we have used in proving channel coding theorem for discrete channels. And what was those ideas? We are going to use randomly we are going to generate this code word, and we are going at the receiver we are going to use typical set decoding. So we are going to use these ideas of random codes and joint typical decoding. As I said, we are going to take into account that now there is a constraint on power. So if that is violated, basically that's an error, and the variables are now continuous, not discrete. So that's the difference from the proof that we have done earlier. So first step is generation of the code book. So we are going to generate a code book in which all code words are going to satisfy the power constraint. So to ensure this, we are going to generate code words with each element identically and independently generated according to Gaussian distribution with variance given by p minus epsilon, where epsilon is a very small positive number. Now by choosing noise variance p minus epsilon, we are going to ensure that the average power constraint is not violated. So we can see from law of large numbers, if we generate each code word normal distributed with variance given by p minus epsilon, by law of large numbers the average value will basically tend to p minus epsilon, and hence the probability that a code word does not satisfy this average power constraint will be small. Let xi w, where w are these 2 raised to the power n minus nr code words, be IIT distributed, and as we said we are generating these code words with variance given by p minus epsilon. So let these code words be xn1, xn2, xn2 raised to the power nr. So these are n length code words which are randomly generated with Gaussian distributed with variance p minus epsilon. So after the generation of the code book is revealed to both the sender and receiver. Now if you want to send message w, what the sender does, it sends the wth code word xnw in the code book. Now at the decoder we are going to do typical set decoding. So how does typical set decoding works? So we are going to see which code word is jointly typical with the received code book, and if there is only one code word which is jointly typical with this and there is no other code word which is jointly typical with the received code book, then the decoder will correctly decode, otherwise there is a decoding error. Also if the power constraint is violated, then also there is an error. So the receiver is going to look down the list of code words which are just denoted by this X and W, and it searches for this one code word which is jointly typical with this received vector Y and W. It tries to find that one code word which is jointly typical with this received vector. Now, if there is one and only one, note this, if there is one and only one such code word, then the receiver, and let's see that code word is X and W, then the receiver is going to declare that the transmitted code word was W. Otherwise, the receiver will make an error. So, if there are either more than one code word which is jointly typical with the received sequence, or there is no code word which is jointly typical with the received sequence, then the decoder will make an error. Also, when power constraint is violated, then also receiver will make a error. So, as I said, the receiver also declares an error if the chosen code word does not satisfy this average power constraint. Now, let us compute what is the probability of error. So, when the decoder is doing joint typical set decoding, let us compute what is the probability of error when we are sending this WH code word over this Gaussian channel. So, without loss of generality, we will assume, let's say the code word 1 was sent. So, we are going to assume code word 1 was sent without loss of generality. Then the received code word Yn is going to be Xn1 plus Zn. This is the noise. This is the code word that was transmitted, and this is what we have received. Now, let us define the error events. The first error event which I am defining by E0 is the error event corresponding to the violation of average power constraint. So, E0 is if the average power constraint is violated, then the event E0 happens. So, this corresponds to violation of power constraint, the average power constraint that we had. Let EI be the event where Xni and Yn belongs to this jointly typical set. So, EI corresponds to the event when Xni and Yn are jointly typical. So, clearly an error happens if event E0 occurs, or if E1 complement occurs. Why? Because we have sent code word 1. So, there will be no error if Yn is jointly typical with Xn1. However, event E1 complement will occur if Xn1 and Yn are not jointly typical, and that's this event E1 complement. So, if the transmitted code word and the received sequence are not jointly typical, that corresponds to the event E1 complement. Then also error happens, or if any of these events occur, E2, E3, E4, E to the power NR. That means if any other code word other than the code word number 1 is jointly typical with the received sequence Yn, then there is an error, and that is denoted by these union of events E2, E3, E4, E to its power NR. So, this corresponds to a wrong code word which was not sent to be jointly typical with the received sequence. So, now that we have enumerated the error events, let us compute the probability of error given the code word 1 was transmitted. So let E denotes the event that W hat, which is an estimate of the code word that we sent, is not same as W, and let P be the conditional probability of error given W is 1. So this is given by probability that event E0 happens, which corresponds to violation of power constraint union with event E1 complement, which is the event that xn1 and yn are not jointly typical, or union with E2, E3, E4, E2 to the power nr, which corresponds to the event that a wrong code word is jointly typical with the receive sequence yn. Now this can be upper bounded using union bound. Using union bound, we can upper bound this probability of union of these events by, so we can upper bound this using union bound. This is probability of E0 upper bounded by probability of E0 plus probability of E1 complement plus probability of E2 plus probability of E3 up to plus probability of E to the power nr. Fine. Next. Now we are going to evaluate these probabilities. Now first let's look at probability of E0. Now remember, we were generating these code books with variance p minus epsilon, where epsilon is a positive number, small number close to 0. So if we are generating our code books like this, by law of large number, probability of occurrence of this event E0 is 0 as n is very large. So this probability can be upper bounded by a small quantity epsilon. Similarly, let's look at this probability of occurrence of the event that E1, that xn1 is not jointly typical with yn. Now we know from the property of joint AEP, which we proved in the last class, that probability of this event is also 0 as n goes to infinity. So this can also be upper bounded by epsilon. So we have upper bounded this by epsilon and upper bounding this by epsilon. Now let us look at this error event. Now since the way we are generating our code books, xn1 and xni, where I is some other code word, they are independent. So yn and xni are also going to be independent, and we have shown that, we have shown a result in the last class that what is the probability that if xn, xni and yn, which are chosen independently, what is the probability that they will be jointly typical? So what is the probability that xni and yn are jointly typical? This we have proved in the last class by the properties of joint AEP. This is upper bounded by 2 raised to the power minus n times mutual information between x and y minus 3 epsilon. So if we let W to be uniformly distributed over all these 2 raised to the power nr code words, then subsequently the probability of error is given by this average probability of error. Now as we said, average probability of error without loss of generality can be written as probability of error given code word 1 was sent. Using union bound, this was upper bounded by some of these error events. We have already shown this is upper bounded by epsilon, this is upper bounded by epsilon, and this is upper bounded by this quantity. This follows from the properties of joint AEP, which we have proved in the last class. So then this term does not depend on I, so I can sum over all i's going from 2 to 2 raised to the power nr. So I get this epsilon will be 2 epsilon, and this summation over I from 2 to 2 raised to the power nr, this will be this term, and then we have this one, which is this. Now combining the terms containing n, I get this. This can be written as 2 raised to the power 3n epsilon into 2 raised to the power minus n, mutual information minus r. And this quantity, if we choose our r to be less than mutual information between x and y minus 3 epsilon, see this term we can write as 2 raised to the power minus n mutual information between x and y minus r minus 3 epsilon. You can write it this way. So if we choose our r to be less than mutual information between x and y minus 3 epsilon, then this term will be positive, and so for large n this will also go to 0. So this whole term can be upper bounded by epsilon. So in other words, this probability of error can then be upper bounded by 3 epsilon, provided my rate is less than mutual information between x and y minus 3 epsilon. So this shows that there exist good codes with rate given by this, and in those cases the probability of error will go towards 0 as n goes to infinity. Now if we delete half of these words, code words, we obtain a code with low maximal probability of error. In particular, the power constraint will be satisfied by these remaining code words, because we are already throwing off these so called worst code words, and hence we have constructed a code that achieves a rate arbitrarily close to capacity and gives probability of error which goes to 0 as n goes to infinity. So this proves the achievability of Gaussian channel capacity. Next we are going to show the converse of the channel coding theorem for Gaussian channel. So we are going to show that we prove that the channel capacity of Gaussian channel is given by this, and we prove that rate greater than capacity is not achievable, or we are going to show that if probability of error goes to 0, then the rate is less than channel capacity. Now the converse proof is very similar to the proof for discrete channel. There is one additional constraint that we have here now, which is the average power constraint. So we are going to show you now that this probability of error goes to 0 for a sequence of code given by these parameters for a Gaussian channel with power constraint P, as long as rate is less than capacity, which is given by this expression. So we are considering a 2 raised to the power nr comma n code which satisfies average power constraint, which is given by this expression, and this is satisfied by all code words, W going from 1 to 2 raised to power nr. Let W be uniformly distributed Now this uniform distribution over this index set induces a distribution on input code words, which in turn induces a distribution on the input alphabet. And we can show that W, X and W, Yn and W hat, they form a Markov chain. So W is my code word index, Xn is my encoded code book, Yn is a received code book, and W hat is an estimate of W based on what I receive, which is Yn. Now we are going to take help of Fano's lemma to relate probability of error and to mutual information. Now we in the class have used this version of Fano's lemma, which was given by we did h of Pe plus Pe log of L minus 1. We use this version, and we said this can be weakened because binary entropy function is less than equal to 1. So this can be weakened as 1, and this can be further weakened as P log of all the possibilities L. So number of code words here is 2 raised to power nr. So if we take log of that, this will become less than equal to 1 plus n times r and probability of error. So this is the version that we are using. Uncertainty in W given W hat is upper bounded by 1 plus nr times probability of error. And as we said, here we are going to show that if probability of error goes to 0 for large n, then the rate has to be less than c. So this is, so uncertainty in W given W hat is less than equal to n times some small value epsilon, where epsilon goes to 0 and probability of error goes to 0. Now W is uniformly distributed over this index set 1 to 2 raised to power nr. So uncertainty in W is given by log of 2 raised to power nr, which is nothing but nr. Now from the definition of mutual information, we can write uncertainty in W in terms of mutual information between W and W hat plus conditional entropy of W given W hat. Now if probability of error goes to 0 as n goes to infinity, we have shown that this term is upper bounded by n times some epsilon. So I can write then uncertainty in W is upper bounded by mutual information between W and W hat plus n times epsilon. Now we just saw in the last slide that W, X and W, Yn and W hat, they form a Markov chain. So then from data processing lemma, we know that mutual information between W and W hat is going to be less than mutual information between X and W and Yn. So this follows from the data processing lemma. So then we can write this, that the mutual information between W and W hat is less than equal to mutual information between xn and yn. So that's what we are writing here, and this comes as n times epsilon n. Now, following the definition of mutual information, we can write the mutual information between xn and yn as differential entropy of yn minus differential entropy of yn given xn, and this is n times epsilon. Now, what is yn? Yn is output of the Gaussian channel, which is xn plus zn, where zn is the Gaussian noise with zero mean and variance n. Now, uncertainty in yn, differential entropy of yn given xn, can be written as differential entropy of xn plus zn given xn, and this is nothing but uncertainty in zn given xn. Now, note that the noise zn and the signal xn are independent, and hence this can be written as uncertainty in differential entropy of z of n. So, I can write differential entropy of yn given xn as differential entropy of zn. Next, so what we have shown so far is nr is actually less than equal to h of yn minus differential entropy of zn plus n times epsilon. Now, this can be upper bounded by this. Again, this is straightforward to prove. We have proved this using chain rule. We can write h of yn in terms of y1, y2, y3, yn condition on these yi's, and we know that conditioning cannot increase entropy. So, from that we get this result. Similarly, we can write h of zn as less than equal to summation over I from 1 to n h of zi. So, this is what we are writing here, plus n times epsilon n. This is this term here. Now, we have just shown h of zi is same as h of zi given xi, and this is same as h of xi plus zi given xi, which is same as h of yi given xi. Okay. So, this is differential entropy of yi, this is differential entropy of yi given xi. So, then this can be written as mutual information between xi and yi. So, from this result and this result, we can write nr is upper bounded by summation of mutual information between xi and yi, where the summation is over I going from 1 to n plus n times epsilon. Now, let xi be wiw, where xiw, where w is drawn uniformly over this index set, and let pi be the average power of the ith column of this code book. We know that xi, the signal, and zi, the noise, they are independent. So, the average power of the received sequence yi can be written as pi plus n, where pi is the power of xi, n is the noise variance. Now, again, this result we have proved in the previous class, that if y has yi's have the same second order moment, the Gaussian random variable will have the maximum differential entropy. So h of yi is upper bounded by the differential entropy of an equivalent of the differential entropy of a Gaussian random variable with same variance. So basically h of yi is upper bounded by half log of 2 pi e times pi plus n. So the differential entropy of yi is upper bounded by the differential entropy of a Gaussian random variable which has 0 mean and variance given by pi plus n. Actually mean can be anything because translation does not change the differential entropy. Okay. Now continuing with the inequalities that we had, we just had the expression that n of r is upper bounded by summation over all i's from 1 to n h of yi minus h of zi. Now we just have now showed you that differential entropy of yi is upper bounded by this quantity, and since zi is Gaussian distributed with variance n, its differential entropy is given by this expression. So now combining these two log terms, this term and this term, we get this expression that nr is upper bounded by summation from I goes to 1 to n half log of 1 plus pi divided by n plus n times epsilon. Now the way we generated these code words, they all satisfied average power constraint. So they all satisfied power constraint because we were generating this code word with variance given by p minus epsilon. So these code words were satisfying power constraint, so their average is also going to satisfy the power constraint. Now we know that log is a concave function, and if a function is concave, we know from Jensen's inequality that expected value of the function is less than equal to function of expected value. So this is what we know from Jensen's inequality if f of x is a concave function. In this case log is a concave function of x. So then here we have this expression that nr is less than equal to summation over all i's 1 half log of 1 plus pi n plus n times epsilon n. Now if I divide this by n, what I would get is this will go away, this will go away, and I will have here 1 by n. So I have this expression r is less than equal to 1 by n summation this term plus epsilon. Now I know that log 1 plus x is a concave function of x. So then expected value of the log function will be upper bounded by log of expected value of this x. So that is what we are doing here. So this is expected value of the log function. This is from Jensen's inequality upper bounded by function is log of the expected value. Alright. Now this 1 by n summation pi is nothing but average power constraint. So what we have shown here now is that r is less than equal to 1 half log 1 plus P by N plus epsilon. So what we have shown is, if probability of error goes to 0, then R is also less than channel capacity. So R is less than channel capacity if probability of error goes to 0 as n goes to infinity. So this proves the converse of the channel coding theorem for Gaussian channel. Next we are going to talk about what is the capacity of a Gaussian channel if the Gaussian channel is band limited to W hertz and the noise power spectral density is given by N naught by 2. So we are going to show you that if the Gaussian channel is band limited to W hertz and its noise power spectral density is given by N naught by 2, then the capacity of this band limited Gaussian channel is given by W log of 1 plus P divided by N naught W. This is the capacity of the band limited Gaussian channel, and if we let W go to infinity, then the capacity is given by this expression. So let us prove this. So if the channel is band limited to W, then we can sample the signal at rate 1 by 2W, and that would be sufficient to reconstruct the signals from the samples. This follows from the Nyquist criteria. Now if the noise has power spectral density given by N naught by 2 and the bandwidth is W, then the noise power is given by N naught by 2 times 2W. So you have basically noise power spectral density given by N naught by 2 and you have bandwidth of W to W. So this noise power is given by N naught by 2 into 2 times W, which is N naught W, and over a period from 0 to t you have so many noise samples because you are sampling at rate 1 by 2W. So each of these 2WT noise samples in time t will have variance given by N naught W times t divided by 2WT, which is nothing but N naught by 2. Now let us use the channel over time 0 to t. So power per sample would be P times t divided by total samples, which is 2WT, and that comes out to be P divided by 2 times W. So similarly we can compute noise variance per sample, just N naught into 2WT divided by 2WT, which is N naught by 2. So capacity per sample is given by half log 1 plus power per sample. This is noise per sample. If you go back here, noise variance per sample is N naught by 2 and power per sample is given by P by 2W. So then the capacity is given by half log of 1 plus P by 2W divided by N naught by 2, and this is nothing but half log of 1 plus P divided by N naught W. Now this is capacity per samples, and how many samples we have per second? We have 2W samples per second. So then the capacity is given by W log of 1 plus P divided by N naught W bits per second. This is signal power, this is noise power. And we can similarly compute, if we let W go to infinity and take the limit, the capacity comes out to be this expression, P divided by N naught into log of E. bits per second. So this is the expression for capacity for band limited Gaussian channel. So with this we will conclude our discussion on Gaussian channel. In the next lecture we will talk about parallel Gaussian channel. Thank you.